Good morning, everyone, and welcome to my presentation. The title is about the Synergistic Valorization of Waelz, Linz-Donawitz, and Fayalite Slags. So this work is in collaboration with different partners from Bethesda, Freiberg, Steinbeis, University of Jyväskylä, Helmholtz, and Recomind. First, I'd like to say that metals play a crucial role in our society. It even became an indicator of how progressive a country is. However, producing metals comes with co-productions of slags. Say, for example, with copper. In a flash smelting furnace, you are producing copper matte and Fayalite slag. Yearly, we're producing 44 million tons of Fayalite slag. And in recycling of zinc, we are producing Waelz oxide, which is the zinc oxide, and also Waelz slag. Every year, we are generating 2 million tons of Waelz slag. And in the steel industry, in the basic oxygen furnace, we are producing steel, and at the same time, the Linz-Donawitz slag. And here, we are accumulating 100 million tons per year. These slags are ending up in landfills, which then become a problem because these contain some residuals of the heavy metals. Without treating them, it will just occupy space in the landfills. How then can we valorize them? One way is through pyrometallurgy. By checking in their chemistry, as what we can see here, all these slags contains the things that we need in order to do smelting. It has Al2O3, CaO, SiO2, and some of the valuables that we wanted. We can actually valorize them. Silicon, iron, manganese, calcium, vanadium, zinc, and copper. So if we imagine in a smelting process, we can have a slag system of SiO2, CaO, Al2O3, and we will have a molten metal of iron, manganese, vanadium, and copper, and zinc can be recovered in the gas phase. Thus, circular economy is applicable in these valuables. How do we do this? First is, from the literature, we have to apply this. In an Al2O3, CaO, SiO2 slag system, the basicity ratio, in order to have a separation of metal and slag, is around 1.0. As long as we maintain this basicity ratio of our charge, we can expect that if the system reaches the molten state, we will have a separation of metal and slag. And from this, we have our plan. We have to characterize first the materials that we receive by using different chemistries, wet and dry. We did ICP, MLA, XRF, XRD, Mossbauer, and carbon-sulfur analysis. And by establishing the chemistry of our charges, we can do a more realistic simulation with FACSAGE. And from there, we can do this experiment. Then we can scale it up from gram scale to kilogram into 100 kilogram scale. And after that, we then characterize the product and check how much recovery we have, and we can further optimize it by simulating again the process. The ratio between these three slags so that we can have a self-fluxing mixture. I did a calculation using R. So I plotted the three slags in a ternary graph. And here we can see the endpoints are the different slags. And I want to identify what is the ratio between these three slags such that the total basicity of that mixture is between 0.9 to 1.0. So I have identified 10 points. And the ratio between these in every mixture are listed in the table. For example, in ID1, it's 6% Linz-Donawitz, 72% Waelz slag, and 22% Fayalite slag. So every point within this ternary is satisfying the basicity ratio of 0.9 to 1.0, and also it's 100% mixture of the three. After I have identified the mixture, I've noticed that actually it's forming a line, which is valuable if you are in a perspective of processing. If you want to make some changes, then we can keep ourselves in this line so that we are confident that we are in the basicity that we wanted. And then this is applicable for an ACS slag system. And I plotted this in PackSage with a phase diagram module. And here in this ternary diagram, I have the 1450 degrees Celsius liquidus region. And I identified the mixture inside the liquidus region, what's the composition inside. And then I used the viscosity module and calculated the viscosity value of that mixture. And then I bring every point into R and then plot a heat map on it and then superimpose it in the ternary diagram. And in this diagram, we can see the viscosity values in different composition inside the liquidus region and also the isoviscosity lines. And here, when we plot the slags individually, it's actually outside the liquidus region, which in a process perspective we do not want. So we have to mix them if we want to be inside the liquidus region. Now, in the target composition is where the location of these 10 identified mixtures. And after we confirm that we are inside the liquidus region, we then did an equilibrium calculation and to further confirm if we are really fully liquid in that composition and conduct a 20-gram experiment on these mixtures. After that, we plotted this in a MgO weight percent in the x-axis and y-axis with a viscosity. So we then image every mixture using a CT scan, and these are the cross-section image of each of the mixture. So here it's noticeable that some are dispersed and some are agglomerated, which we will discuss further. And our criteria in choosing which of these mixtures performs the best is the biggest single nugget formation. Then we have identified that ID7 and ID9 have the biggest single nugget form. And the main takeaway we have here is that the MgO weight percent is directly proportional to the interfacial tension. And interfacial tension is crucial because it promotes the formation of larger nuggets. Now, in the region where there is low surface tension or interfacial tension, we have observed that it's actually a bit dispersed. Sorry, yeah, here. So these ID1 and ID2 are the region where the MgO is low and the viscosity is high. So the gray is the slag in this image, and the blue is the metal. Since it has low surface tension and low interfacial tension, the metal droplets are smaller and dispersed into the slag. In the region where we have high MgO, thus high interfacial tension and high viscosity, we are forming larger nuggets. And since it's larger nuggets, it was able to settle. And we have identified between these two that ID9 is the bigger nugget. And if we observe the spatial location of these, ID9, the nuggets are located more in the bottom than the ID7. Thus, we have scaled up ID9. So if you want to know further about this work, you can scan this QR code and read the paper. And here we have scaled up ID9 into a 2 kilogram experiment. And we have cracked the crucible and check it again. Here is the cross-section image of the crucible plus the charges and the slag and the metal. Then we separate the metal and the slag. And this is why we wanted to have the single nugget in the bottom of the crucible, so that we will be able to recover the metal later on in the process. And in this scale-up, we have 98% recovery of iron, copper 96%, vanadium 91%, and manganese 46%. It is a really high recovery process. And how can we play this? Can you play the? Yeah. Yeah, so here is where we are in the topping stage of the scale up of 100 kilogram process. And yeah, we are able to tap since we are in the low viscosity mixture. And after confirming this, we then conducted a life cycle assessment with a cradle to gate scope. And here is the scenario analysis. First is that we check if the furnace is at our institute, we have to transport the slag, so the charge is at room temperature. And another scenario is when the furnace is directly outside the kiln, so we can utilize the exit temperature of the charges, and then that's the scenario 2. Now we have a flow sheet from HEC, where the feeder will do the mixing and then feed it to the plasma furnace, and then we then produce the pig iron, and then the slag from the furnace we process again to remove the sulfur, and the flue gas will go to the thermal oxidizer, the cooling tower, and later on to the scrubber to produce the gypsum, and we will recover the zinc oxide in the cooling tower. After this, we calculated what's the input needed, and then we calculated what's the CO2 emission in each of the processes. So here is the CO2 emission in every unit processes. And we have identified that most of the impacts are in the plasma furnace. Actually, that's 79%. Maybe it's the converting. Yeah. So it's in the plasma furnace, 79% of the CO2 emission, and followed by the scrubber and the feeder. In the case of the scrubber, it is because it was there where the process emission was accounted. And for the feeder, it's where the reductant, the pet coke, and also the transportation of the slags were accounted. So it's clear here that the main emission was in the plasma furnace. It's because of the electrical demand and the argon requirement of the furnace. Now what we did is calculate the avoided burden by doing this recycling and by having also the full utilization of the products. And in the first scenario, we are emitting 23,000 kilograms of CO2, and in the second scenario, 15,000. And the avoided burden is 9,000 in both, with a total emission of pig iron production. So we have calculated up to how much CO2 emission we are emitting per ton of pig iron. And for the scenario 1, we have 3.96 tons CO2 per ton pig iron. And for scenario 2, when we utilize that heat from the furnace, we have 1.68 ton CO2 per ton pig iron. And this is actually lower or comparable to the 1.73 ton CO2 per ton pig iron emission in the average of the primary production. In conclusion, we are able to identify the self-fluxing feed mixture. So in this process, we just utilize the slags. We did smelting, we recover the product, zinc oxide, pig iron, construction grade slag, and gypsum. Thus, we have a holistic approach on the slag, and a circular economy has been applied. So I'd like to thank everyone for your attention, and also the BMFTR for funding this project. And if you'd like further information, you can contact us, myself, Rafaela, and Volker, and Ajay for further information.